Okay, this is section 2.1. We're going to start getting into some of the applications of the derivative. And in specific, we're going to classify maximum and minimum values as well as define increasing and decreasing in this particular section. So as you can see, our objectives are to find relative extrema of a continuous function using the first derivative test and to sketch graphs of continuous functions. So some of the vocabulary I already mentioned: increasing and decreasing, something which is called a critical value, relative maximum and relative minimum, extreme values, and the first derivative test. There's a lot of vocabulary here, and that's probably the more important thing because I think the concept is going to be relatively easy for people to understand. It's just about putting the vocabulary together with the concept so you know what it is you're looking for. Okay, so let's go ahead and take a look at this graph below. The graph represents product sales during the first 5 months of 2017 from 0 to 5. We would like to know when the sales are increasing, when the sales are decreasing, and any particular day on which the sales peaked or hit a slump. You probably can look at this graph and figure that stuff out pretty easily. So it's all about just putting it together in the right notation and, again, making sure you understand the vocabulary. If you look at the graph, it's got product sales on the left, time and months on the bottom. So it is how much sales over the increment of time that you're going to have. It should be pretty obvious, or at least I think it's pretty obvious, that the sales are increasing starting right here at the origin, and then all the way up until it gets to right up here where I put the green dot at the top. Excuse me. That seems to be pretty obvious. A graph is read from left to right, so the product sales keep going up and up and up from 0 up until you get to someplace in between the time of 1 and 2 months. Looks like 1.3 is what they put in parentheses there. So that will be our first interval of increasing. So number 1 here says, on what intervals is the function increasing? Well, it's increasing starting at 0 all the way up until it gets to 1.3. Okay, and the interval is going to be done based upon your independent or your x-axis. So you're going to write that as interval notation. It looks like an ordered pair. It's not. It's interval notation. It's saying that every value from 0 to 1.3 on the x-axis is going to show an increase in sales. Okay, I'm going to have to scroll back and forth just a little bit here. You don't have to do that on your own paper, obviously. On what interval is the function decreasing? Okay, well, decreasing should also make sense. That's where the graph would be going down. So starting basically where we left off at 1.3 all the way until we get down here to 3.3, the function is decreasing. As a matter of fact, I'm going to go back for a second here just to kind of show that this is increasing. I'm just going to highlight it with arrows there going up. And then this one is decreasing because it is coming down. Again, hopefully you can see that and that makes sense. So my first interval of decreasing is going to start at 1.3 and then it's going to go to 3.3. Notice I'm putting parentheses around these, by the way, because at 1.3, at the very top there, it's not increasing or decreasing. We can't really say it's doing one or the other. At the bottom, at 3.3, it's not increasing, it's not decreasing. We can't really tell which one it's doing. So that's why I use a parentheses as opposed to like a squared off bracket in this case. But these aren't the only intervals of increasing and decreasing. As you can see, the function then starts to go back up. So now we're going back up until we get to 4.7. So I have another interval of increase. So we're going to put that there's a union here because there's more than one interval of increase. And it's going to go from 3.3 up until 4.7. Whoops. I don't know why I ended the parentheses there. It's 3.3 to 4.7. There we go. And then it looks like we're going to have a decrease. Now, this thing goes off the graph, so what we have to assume here is that it's going to keep on going. So we are going to have a union of decreasing interval. It looks like it's going to pick up at 4.7. And then according to this graph, it looks like it's going to go off to infinity. So we're just going to go ahead and put that off to infinity. Does the function have a relative maximum, a relative minimum? If so, what are they? What are the relative minimums? Well, a relative minimum does not mean that it's the smallest, most place on the graph. It means within a certain area, is there a minimum value? So if you isolate it, can you find a place where your graph goes from decreasing to increasing? That would give you a relative minimum. Well, there is a place on this graph where this function goes from decreasing to increasing, and it's surrounded right there. Okay, you can see if you just look in between those orange parentheses kind of that I put there and ignore the rest of the graph is going to have a minimum value. It's going to have a bottom. And it does say it wants to know what the minimum is. The minimum is the y value. When it asks for a max or a min, it's the y value. You can state where it is by saying at x equals. That's fine. But don't give me the x value. The minimum and a maximum of a graph are the y values. So in this case, the relative minimum is 3.95. So we're going to say the relative minimum is 3.95. And once again, what we can say is if we want to describe where it is, it's at x equals, what is that, 3.3. 3.3. And that looks like it's the only place where we have a relative minimum. You might say, well, what about this piece right here over at 0? That looks like it's the bottom, but it never goes back up. To be a relative minimum, it must change direction. It's got to go from down to up. Okay. Likewise, to be a relative maximum, you're going to have a change from up to down. So it looks like on my graph, I have two of those. I've got one that looks like it's right here, changes from up to down, and then it looks like I've got one right here, which also changes from up to down. So I'm going to have a relative maximum of, was that 404? So I've got a relative max of 404 at x equals, that was the first one, so that was at 1.3. I have another maximum, so and relative max of 209 at x equals 4.7. For some reason, my decimals keep dragging. That's a 209 right there. Okay, again, I think you guys can probably see that just by looking at the graph. It's not really, I don't think, terribly difficult to figure out. Basically, you're looking for peaks and valleys. Again, it must change direction to have a relative. At the endpoints of a graph, you cannot have what's called a relative maximum or minimum. Okay, it's called something else if there is a max or min there. We'll get to that. All right, so when a function is increasing, its tangent lines have positive slopes. So I'm going to try and go back and highlight this in blue here. If you look at where this thing had green arrows going up, all of the tangent lines, it's kind of hard to draw this, but all of the tangent lines here, if I were to draw a tangent line, little mini tangent lines, all the way up to here are positive. But then when it starts coming back down, now my tangent lines, which hit the outside of this curve, are negative. Okay, that is a very important concept. Okay, you can see all the tangents that go up are positive, all the tangents that go down are negative. And tangent lines can be found by derivatives. So when we have a tangent line which has a positive slope, it's because the derivative is positive there. Because derivative is a slope, if you've got a positive derivative, your function is increasing. Likewise, because again, derivative is a slope, if you have a negative derivative, then the function is decreasing at those points. So the theorem down here is exactly what I just said. If f prime is greater than 0 for all x, then f is increasing on that interval. If f prime is less than 0 for all x, then f is, that is a typo. Should say decreasing. Whoops, sorry. That is a typo. That should say decreasing. So go ahead and fix that. A big time note here. Note that the statement, if f is increasing, then the derivative is positive, is not always true. We'll actually explore some of those examples in the next page. Okay, so let's go ahead and go to the next page. All right, so here you have a graph, and we've gone ahead and labeled a bunch of the tangent lines at specific places just to make it easier to see. Looking at the graph, note f prime of x equals 0 at the following places: C1, C2, C4, C7, and C8. That's where you have a horizontal tangent or a derivative of 0. F prime does not exist at C3, C5, and C6. As you can see at C3, you have a vertical tangent. At C5, you have a corner. And at C6, you have a cusp. So in those cases, there is no derivative, as we have talked about in previous sections. And as you can see, the function changes from increasing to decreasing, or vice versa, at C1, 2, 4, 5, 6, and 7. The function has a relative max and a relative min at exactly these points and no others. So here is the easiest way for you to figure out whether something has what's called a critical value. A critical value basically is something is really important happening on your function, and we find that by one of two ways. Either f prime of c equals 0, or f prime of c is undefined or does not exist. And remember, a vertical slope is technically undefined, therefore it does not exist. So in the graph of f, C1, 2, 4, 7, and 8 are critical values because f prime of c, or the derivative, equals 0, meaning the slopes are horizontal, which you can see at all of these places. Okay, I'm not going to do them all, but you get the idea. And then at C3, 5, and 6, those are also critical values because f prime does not exist. So at C3, 5, and 6. At C3, right here, vertical tangent, so it's an undefined slope. C5, corner. C6 is a cusp. So all of those places are critical values. Okay, I'm just going to go ahead and do what I said I wasn't going to do. I'm going to finish off. These were the horizontal ones. May as well. Okay. So as we saw in the graph, just because a value is a critical value doesn't mean that it has to be, that it has a relative max or minimum. At the point C3 and C8, and I'll scroll back up in a second, that's the case. But if f has a relative max or min at a particular value, it will be a critical value. So if we can guarantee that it's a max or min, it's going to be a critical value. But just because it's a critical value doesn't mean it's a max or min. It's kind of one of those, you know, square, rectangle, rectangle, square thing. One indicates the other does not necessarily mean the converse. So as you can see, again, at C3, there is a critical value, but that's not a max or min. At C3, right here, that's a critical value, but it's definitely not a peak or a valley in the function. Okay, just to make sure you guys understand that. Oh, and I forgot C8, sorry. At C8, once again, this is a horizontal slope, but as you can see, the direction does not actually change right there. It actually goes from increasing and then it starts to increase again. So it does get to a horizontal slope, but it doesn't change direction as far as the increasing and decreasing is concerned. Okay. So we can also use f prime to determine whether a point has a relative max or a relative minimum. And in general, here's the idea. If f has a relative maximum at c, so, and I'm going to sketch this down here. If f has a relative maximum at c, think about this. Just in general, your function's got to go from up to down, and right there would be a relative maximum, which means that f has to be going up to the left of c, which means it has to be increasing or positive. Well, I'm sorry, positive slopes. And then f has to be decreasing to the right of c. Likewise, for you to have a minimum value, that means you have to have something at the bottom, which means that in order for this to be a minimum, to the left of c, the function must be decreasing. And then to the right of c, the function must be increasing. Hopefully that makes sense. So in order for you to have a max, the function has to go up to down. In order for you to have a min, the function must go from down to up. Okay, so let's put all that together and use what's called the first derivative test for finding relative max and minimum values. It's really not that difficult of a process, and you'll get used to it. It's actually one of the more common processes, something like that, when it comes to calculus. First thing you do is you list all the critical values, which means you need to take a derivative of your function. Or at least have some way to identify the derivative at specific places. So you're going to test the function to see whether f prime equals 0 or whether f prime just doesn't exist. Those are going to be your critical values. You find those first. Then you can make a table, and there's different ways to do this, and everybody does it slightly differently. You can make a table of the f prime values, and we'll show the example below. And then you're going to draw your conclusions about specific values in the table, which is going to help you to determine whether you have maximums or minimums. Again, if f is increasing to the left and then decreasing to the right of a critical value, it's a max. If it's decreasing to the left and then increasing to the right, it's a min. If f has the same behavior on both sides of c, meaning it goes from increasing to increasing or decreasing to decreasing, then f does not have a relative extreme value at either one, at C. Okay, and again, your textbook shows it in a slightly different way. I'm going to try and show you this way. I'm going to show you one additional way that I do it, and I think it's just as easy. You can use whatever way is most comfortable for you. All right, so here is our example. Find the relative maximums or minimums of this specific function right here. Well, the first thing you have to do is you have to take the derivative. Once you take the derivative, you want to know where that derivative is either equal to 0 or it is undefined. So we take the derivative, which we now show right here, which is f prime of x. And that's a polynomial, and since it's a polynomial, there's no way that this cannot exist. So we're just going to set it equal to 0, so we're f prime of x equals 0, and we're going to solve it. Once we set it equal to 0, a little bit of factoring. First step, we divided a 6 out of everything right here. It doesn't actually show that process, but we divided the 6 to get from step 1 to step 2. And then we factored. Once we factored the quadratic, you get x plus 1, 2x minus 5 equals 0. Set each factor equal to 0, and we get that x equals -1 or x equals 5/2 are our critical values. So we list those as -1 and 5/2. Well, no matter what your function is doing, since those are the only two critical values that we found, everywhere else on the function must be either increasing or decreasing. And in order for a function to change its direction to go from increasing to decreasing or vice versa, it must hit a critical value somewhere. Well, since those are the only two critical values, it's safe to assume that once you find something that's on either in between those critical values or on the outsides of those critical values, it will always do exactly that same thing. What does that exactly mean? Okay, so we're going to break this up into basically a real number line. The intervals that you see here are, first of all, I've listed our critical values, which is -1 and 5/2 numerically. Make sure they're listed numerically left to right. And then at those, the derivative was 0. That was the easy part. Well, anything to the left of -1 on the number line basically keeps on going to negative infinity. Again, whatever this function is doing, it's going to be doing that all the way up until -1. Cannot change direction because it would have had to have had another critical value. So from negative infinity to -1, all I need to do is I'm going to take any value that I want to and figure out what my slope is doing. So pick something easy like -2. If I was going to plug in -2, I'm going to come back up to this specific step right here. Okay, now this is what I call a sign analysis step. If I were to plug -2 into this x plus 1, I don't really care that it's going to give me -1. It will. What I really care about right now is that it's going to give me a negative value. So if I plug -2 into x plus 1, it gives me a negative. If I plug -2 into 2x minus 5, it also gives me a negative. And ultimately, I'm going to take those two negative values, whatever they are, and multiply them. Well, when you multiply two negatives, you get a positive, which tells me that this is a positive value right there. And since the slope is positive from negative infinity to -1, that means that the function is increasing. And I know this is down below, but I'm just filling it in anyway, just to show you. All right, let's pick something in between -1 and 5/2. As a matter of fact, let me just see if that's the values that they used. Oh, they didn't specify values down there in the chart. That's okay. Let's pick something in between -1 and +5/2. If I can use 0, I'm usually going to use it, so let's use 0. Once again, we're going to take 0. We're going to plug it in here. If I plug 0 into the first parentheses, I'm going to get a positive value. If I plug 0 into the second parentheses, I'm going to get a negative value, which gives me a positive times a negative, which is a negative. Therefore, decreasing. See if I can write that better. Decreasing on that interval. And then, as you might guess, although it's not always the case, so you definitely need to check, in the last interval, I'm going to pick something which is greater than 5/2. 5/2 itself is 2.5, so let's pick 3. If we plug a 3, once again, back into these, 3 plus 1 is positive, 2 times 3 minus 5 is positive, so this whole thing is positive, which means increasing here. Oh, they did pick values, I'm sorry. They picked p equals -5, 0, and 10. Well, the 0 was the same, but they just picked -5 instead of my picking -2, and they picked 10 instead of my picking 3. But it all works out to exactly the same thing, positive, negative, positive. So there's your chart. So the big key, and again, you can see it already filled in. I'm just going to keep going ahead and filling this in, is right here. If I go from increasing to decreasing, that means this has to be a max. And the second one, if I go from decreasing to increasing, right here, that means this has to be a minimum. All right, I hope that makes sense. So our conclusion at the bottom is that the point -1, -1, f of -1, which is -1, 42. How did I get the 42? You have to plug -1 back into the original function to get that value. So this is a y value from the original function. Okay, plugging -1 back in is not terribly difficult. Plugging 5/2 in the second one in, a little bit more challenging to do mathematically, but you end up with -175 over 4, and that one is your relative minimum. All right, we're going to go ahead and do a couple of these examples. I apologize, this video will be a little bit longer because they do take a little bit of time, but we're going to get a couple of these examples done so you have some concrete stuff to look at. All right, our first example, we want to find the relative maximums and minimums of f of x equals 2x cubed minus x to the fourth. So the first thing we need to do is take a derivative, find f prime of x, which in this case is 6x squared minus 4x cubed. Once again, that's a polynomial, therefore it's never going to be undefined in this case, so all we have to do is set it equal to 0. And we're going to solve it. So it looks like I've got a 2x squared in common. Let's factor that out, which is going to leave a 3 minus 2x inside. Setting each one of those things equal to 0, 2x squared equals 0. 3 minus 2x equals 0. In the first one, I can divide both sides by 2, leaving me x squared equals 0, which just means x is equal to 0. And in the second one, I'm going to have to, let's see, I can add 2x to both sides and then divide by 2. So x is going to be 3/2. There's the critical values. Now, this is where my method is going to slightly different than the chart. Again, you can choose whichever way you would like to. I simply draw a number line. And I'm going to go ahead and write 0 and 3/2 in there in numerical order. And now we're still going to do the same thing. We're still going to do the testing, but it's kind of a simpler way of doing it rather than writing out the entire chart. So I'm going to pick some value which is less than 0, like -1. And I'm going to plug it into this form. I don't typically go back to the derivative unless I have a much more complicated one. I go to the simplified factored form because for me it's easier just to use sign analysis. If I were to plug -1 into 2x squared, well, squaring -1 gives you a positive, so that's positive. Then I have to plug the -1 into here. Well, that's going to give me 3 minus 2 times -1, but -2 times -1 is +2, so 3 plus 2 is positive. So I get a positive times a positive, which gives me a positive value. That means increasing. Instead of writing the word increasing, yes, I know I'm getting lazy, I just put a little arrow which shows that it's going up. That tells me increasing. Again, this is my method. You can use the chart if it's more helpful. It's completely up to you. Now I'm going to pick something in between 0 and 3/2. Well, an easy number to deal with is 1. So once again, if I plug a 1 into here, that's positive. If I plug a 1 into here, I now get 3 minus 2, which is still positive. So the function is still increasing. That should tell you something interesting is happening at 0. We'll come back to that in a second. All right, last one. I'm going to pick something greater than 3/2, like +2. If I plug a +2 into here, it's still going to be positive. Now if I plug a +2 into here, that's going to be a little bit different because now I'm going to get 3 minus 4, which is a negative value. So now I have a positive times a negative. So now, I'll use a different color here. That's negative, which means that the function is now decreasing. So what I've actually done is I've found my intervals of increasing and decreasing, and by doing so, if you kind of look at the arrows, it tells you where you have maxes and mins. Well, I don't have any minimums. This function never goes down to up. But what you should be able to see is right here, the function goes from up to down. So I do actually have a relative maximum, and it's going to be at x equals 3/2. Remember, however, that is not the actual maximum. I have to plug 3/2 back in, so the actual relative maximum is f of 3/2. Which I'm going to go ahead and just plug in real quick here, and let's see what we get. And that works out to be 27/16. So the relative maximum value is actually 27/16. And there is, in this case, no relative minimum. All right, one more. This one is going to introduce something that we hadn't seen yet in the other ones. Okay, so we're going to find the relative max and min. So let's take our derivative. So f prime of x. Now, this one is going to incorporate a small chain rule, even though it really won't come into play. We bring the 2/3 out to the front, reduce 2/3 by 1, so now I've got negative 1/3. And then I have to multiply that by the derivative of the inside, which is just 1. So that was kind of our chain rule. But we're going to want to rewrite this one. Now, this is where you do want to be able to simplify because it's really going to help. So I'm going to rewrite this. Now, a negative exponent brings everything to the denominator, or basically makes it change its side of the fraction bar. So we're going to rewrite this one as 2 over 3 times x minus 3 to the 1/3 power. All right, so remember that in order for something to have a critical value, it's where this thing equals 0 or where it's undefined. Well, in order for a fraction to equal 0, the numerator must equal 0. There is no way for this fraction to equal 0 since the numerator is 2. There's no variable in the numerator. So this cannot ever equal 0. But the variable is in the denominator, and something which divides by 0 could give us undefined. So what we need to do is we need to take the denominator and set it equal to 0 to find out what might give us an undefined derivative. So we can divide both sides by 0. And then we can cube both sides. Fortunately, 0 on the right makes this really nice. 0 cubed is still just 0. So now I can solve this for x, which means that x is 3, is going to give me an undefined derivative. That's still a critical value. So once again, we're going to use the number line. Fortunately, there's only one value to put on the number line, and that's 3. Okay, so let's figure out what's happening to the left of 3 and to the right of 3 to see whether we have a max or a min, or neither. So we still have to test this into our derivative. We have to test these values because we need to know what the slopes are doing. All right, so I'm going to pick a number like 2. So if I plug a 2 into here, well, what that's going to give me in the denominator is 2 minus 3, which is negative 1, to the 1/3 power. Well, that's a cube root. So cube root of negative 1, because it's a cube root, you can still do it, is negative 1. So you're going to get a negative in the bottom and a positive on the top. Again, I don't really care that it's going to end up giving me negative 2/3, which is what it gives. But what I really care about is the fact that it's negative. So it gives me a negative value here, which means the function was decreasing. Now I'm going to plug in something which is greater than 3. Again, make it something easy, like 4. If I were to take a 4 and I plug 4 into here, 4 minus 3 is 1. The cube root of 1 is 1. So we're going to get positive 2/3 out of that, which means we have a positive value. Therefore, the function is increasing. So it looks like we have a relative minimum because my function goes from down to up. Here's what you have to double check. Because 3 ended up being, okay, I have made a really big mistake, and I'm hoping that you guys have caught this. Some reason I changed that inside from a 2 to a 3. I need to go back and change all these because that is really going to make a big difference here. I apologize. Let's change all those 3s. And that means we have to also change this 3. Okay, these are all 2s. Not sure what I was doing there, so I apologize. Hopefully that doesn't change what we've done too much. Well, it's obviously going to change a little bit. It still is decreasing to the left of 2. It's still going to be increasing to the right of 2. You can use slightly different values, but you will still find that to be the same thing. Here's the major thing. Does 2 actually exist on our graph? Yes, it does. And how I would know that is I would go back to my original, plug 2 in, and see that that actually gives me a value. Well, it's going to give me 0 to the 2/3 power, which is 0 plus 1. So I still have a critical value there. It just means that more than likely this thing is going to be a cusp, but because the derivative doesn't exist there. So it's some kind of a corner or a cusp there. All right, so I can clearly see from what I've done here that this is going to be a minimum. It goes from down to up. So what we have is we have a relative minimum, and the relative minimum at x equals 2 is f of 2, which is going to be equal to, again, I've already done this part, but you plug 2 back into the original function, and you're going to get 1. And in this case, there is no relative max because it never goes from up to down. All right, that is a plenty long enough video. I apologize for the length of it. Hopefully this makes sense. Again, this is a very, very important section, so make sure you take the correct time to figure this stuff out.